Most of us have used microphones, but today we are going to zoom in on this tiny component that quietly powers our earbuds, smartphones, smart speakers, and every voice assistant you have ever spoken to, a digital MEMS microphone. In this video, we are taking a clear look at one such mic, the ICS43434 from INVENSense. We will explore its pinout, common PCB module schematic, and understand what the datasheet is actually telling us. And yes, toward the end, we will also compare it with a couple of similar MEMS sensor. In the upcoming videos, we will connect this microphone ICS43434 to our ESP32 controller, record audio, and even play it back using a Python script. So if you enjoy the occasionally boring but deeply satisfying engineering breakdowns, this video is for you. If not, well, you might want to jump off this video train right here. Namaste and welcome to Avinashee Tech. Today I have two modules with me here, one with a compact PCB size and the other one slightly larger. Both use a small surface mount MEMS microphone package along with just a few passive components. Unfortunately, first module looks a bit ugly after I accidentally burnt one of its solder pads. But don't worry, it's working fine. Look closely and you will see a tiny silver can-like structure. This houses the two key elements, the ASIC. This is a tiny chip that performs amplification, uses ADC, digital filtering, and output formatting. Next is the transducer. This is the physical MEMS diaphragm that converts sound waves into electrical signals. The ASIC, or the integrated chip, then processes those signals and outputs a digital audio. Let's talk about pinout. So this module gives us 6 pins of the MEMS microphone, VDD and ground for power supply, and the other 4 pins for I2S digital audio. Digital MEMS microphones, depending on the type, they output data as PDM, TDM, or I2S format directly. The whole analog front end, preamps, ADC, and the digital part, that is filters, sits inside the MEMS package. So from your point of view, it's just a digital signal which is ready to be processed or streamed by a controller. The 4 I2S pins are BCLK or SCK. This is the main serial clock. Then we have DOUT or SD. This is a digital audio output. LRCL or WS. So this is left-right clock or word select or audio sample rate clock. SCL or LR. So this is channel select pin. So when WS or audio sample rate clock polarity is low, the mic sends left channel data. When the polarity is high, it sends right channel data. So basically, WS clock polarity alters between the channel slots. The SCL pin or the channel select pin decides which channel this microphone will occupy. So if the channel select pin is low, microphone outputs on the left channel. If it's high, microphone outputs on the right channel. For stereo recording, one mic's channel select pin is tied to ground and the others to VDD, both sharing the same data line. Also notice the WS signal changes one clock cycle before data output begins, and data updates on the trailing edge of the serial clock. Okay, alright. If you have a closer look, you will see a small hole on the PCB, larger than a normal via. Nothing to worry about. This is the acoustic port, the pathway through which sound enters the MEMS diaphragm. The ICS43434 is a bottom port microphone, so the PCB hole must align properly with the mic's port. So yes, the microphone may be rated from 60 Hz to 20 kHz, but its real-world response is not flat or equally sensitive throughout the frequency range, and heavily depends on your PCB design and enclosure resonance. As discussed, we have two modules with us today, and both of these modules follow a bit similar simple schematic. So let's start with this green PCB first. So we have one SMD decoupling capacitor between VDD and ground source. Then we have the MEMS package, and on that chip, the SD pin is a tri-state pin. So a pull-down resistor is provided to discharge the main SD line when no device is driving the output, or in simple terms, when all devices are in high impedance state. Lastly, a 6-pin header for connections is available. So that's it. Extremely simple. Similar to the first green board, we have our black PCB board here, and this is a tiny one, but this time we have two decoupling capacitors for a much cleaner supply. The channel select pin is tied to ground through a resistor, thereby defaulting our microphone to the left channel. Similar to last time, we have a pull down resistor on the SD pin because of tri-state logic, and in the end we have our same 6-pin header pins connected. Let's open up the ICS43434 datasheet. Right in the description, the microphone is identified as a bottom port digital MEMS microphone with a 24-bit I2S output interface. Looking at the simplified block diagram, on the left, sound enters through the acoustic port. The MEMS transducer converts the sound pressure into an electrical signal. This analog signal is fed into an ADC, which digitizes it. The ADC output passes through digital filters. Finally, the data is sent out through the I2S serial interface. There is also a hardware channel selection pin to choose whether the microphone outputs data on the left or right I2S channel, and a power management block to support both high performance and low power modes. The microphone is omnidirectional. We have 1.6 to 3.6 volt of operating voltage, making it flexible for low power systems. Sampling rate is set to 48 kHz for the stable, which fully covers the 20 kHz audible bandwidth and satisfies the Nyquist requirement. Sensitivity is -26 dBFS with plus and -1 dB tolerance. Signal to noise ratio is 65 dB A weighted. Equivalent input noise is 29 dB A SPL. Dynamic range 91 dB. THD 1% at 105 dB SPL. Power supply rejection PSR is 99 dBFS for a 100 mV peak-to-peak square wave, and PSRR is -106 dBFS for a 100 mV peak-to-peak sine wave. AOP or acoustic overload point is 120 dB SPL. The digital noise floor is -90 dBFS, again A weighted. Current consumption is approximately 490 microampere and 550 microampere is the max. So remember, dBFS is the digital full scale reference, dBSPL is the acoustic sound pressure level reference. In low power mode, all acoustic performance parameters are nearly the same except current consumption, which is roughly half of the high performance mode. Also, in the digital microphone specifications table, we can see that the supported sample rate depends on the power mode. So high performance mode supports higher sampling rates and low power mode supports a smaller sampling range to reduce current consumption. The microphone accepts a wide range of input clock frequencies from the master device. Clock period is between 303 nanosecond to 2500 nanosecond, which corresponds to a frequency of 3.3 MHz to 0.4 MHz. This flexibility allows the ICS43434 to work with various sample rates. I2S serial clock is calculated using the formula BCLK is equal to number of channels multiplied by sampling rate multiplied by channel width. So for example, if we want a sample rate of 16 kHz, channels is at 2, which is standard I2C format, channel width would be 24 bits, and then if you put that in the equation, we get 0.768 MHz. The master device will generate this clock and it is well inside the supported range of 0.4 MHz to 3.3 MHz. So the microphone will operate correctly at 16 kHz sampling rate. The datasheet also specifies critical timing requirements including SCK high and low times, which is minimum 50 nanoseconds, WS setup time before the first bit is valid, and hold time after the last bit, data valid setup and hold timing. This ensures reliable data sampling by the I2S master. Scrolling further, the datasheet lists the pinout, which includes the pins that we have already discussed earlier. Finally, let's talk about the digital filters inside the ICS43434. The microphone has two main digital filters, a high-pass filter and a low-pass decimation filter. The high-pass filter removes low-frequency components such as the DC offset and mic trip. The important thing to note is cutoff frequency is set to 24 Hz, and this does not scale with the sampling rate, which means that even if you change your sampling rate from 48 to 16 kHz, the cutoff remains fixed. Next, the microphone also implements a low-pass filter and decimation filter, which does two important jobs. Anti-aliasing. There is digital filter before the analog signal reaches ADC, and this filter removes frequencies that would cause aliasing. We have already discussed what it is. Decimation. The ICS43434 uses sigma delta ADC internally. This ADC samples at a very high oversampling rate, typically in the megahertz, which creates a high rate bit stream. So decimation is the process of downsampling this high rate ADC output and converting it to standard audio sample rates like 48 kHz or 16 kHz. A simple way to imagine decimation is the ADC takes many high-speed samples, the decimator combines, averages, and then filter processes those samples and outputs clean, lower rate audio samples. This reduces audio sample data size dramatically while preserving all audible information. Let's quickly open the data sheets of two other digital microphones. INMP441, another popular I2S microphone from InvenSense, and MP34DT05, a PDM microphone from ST Microelectronics. For simplicity ahead, I will refer to ICS434 as 434 only, INMP441 as 441, and MP34DT05 as T05. I mean, come on, I cannot take these names frequently. It's tiring. So 434 has a bottom port, 441 has a bottom port again, T05 has a top port. Port location doesn't affect sound quality much, but it does matter in mechanical design. All these three are omnidirectional microphones. Sensitivity. 434 has minus 26 dB fs, plus minus 1 dB, 441 plus minus 3 dB, T05 plus minus 3 dB. So clearly 434 wins because of its tighter sensitivity tolerance. SNR. 434 has 65 dBA, 441 61 dBA, T05 64 dBA. All three of them are A-weighted, but bandwidth for T05 is not specified. So 434 again comes out ahead. EIN. 434 has 29 dBA SPL value, 441 has 33 dBA SPL value, and for T05 we don't have anything specified. So lower EIN is better, and again 434 wins. Dynamic range. 434 has 91 dB, 441 has 87 dB, T05 again not listed. So a higher dynamic range means better handling of quiet and loud sounds together. So 434 leads again. THD for 434 is 1%, for 441 it's 3%, for T05 not directly comparable again. So once again 434 has lower distortion. Acoustic overload point or AOP. 434 has a value of 120 dB SPL, same for 441, but T05 has 122.5 dB SPL. So here T05 actually wins, handling the loudest sound before distortion takes place. PSRR. So for 434 it's minus 106 dB fs, and for T05 it's minus 90 dB fs. 434 is better here, and 441 doesn't specify. So let's have a look at the final scores. If you look at almost every meaningful audio metric, better sensitivity tolerance, higher SNR, lower noise floor, higher dynamic range, lower distortion, better PSRR, ICS43434 is the clear winner overall. But then it all comes down to application requirements, digital output format preferred, and availability of component, etc. etc. So let's wrap it all up. We started with the module Pinout schematic, explored the ICS43434 data sheet, and finally ended with a three-way microphone battle royale, where the ICS43434 clearly came out on the top. And that is exactly why this MEMS microphone is worth investing in for our tutorials. If you made it to here, you are absolutely awesome. And yes, don't forget to like, share, and subscribe the channel. if you are new here. In the next video, we will connect this microphone to the ESP32, go through the code and record real audio so you can hear the results later on. This is Avinashee Tech. Over and out.